Hi everyone, and welcome back to this series of solving PEO exam problems for Electrical A5 Electronics course. This is a question about BJT transistor, and this question appeared in May 2017, December 2017 tests. And this is also a DC bias question. In the previous question, we had also a couple of DC bias problems, but here this is a bit different because here we have two transistors. One NBN transistor Q1 and one is BNP transistor. Here we are giving all values of the resistors. We are giving the DC bias voltage VCC, and we are giving the beta, and we want to find all voltages VB1, VE1, VC1 for transistor 1, VB2, VE2, VC2, and all currents as well. So how to handle this question? This question, to be able to solve it, you have to split the two transistors. You have first to deal with transistor 1, and then you deal with transistor 2. How you can disconnect them? We know this is your IB2. We know that IB2 is very, very small current compared to the IC1. Okay, so this is your IC1, and this will be almost equal to IC1 because this current plus IB2 will be IC1. If IB2 is very, very small to IC1, which is expected, and we'll see the values to confirm that, then you can assume that this is all of it is IC1. The current that goes through RC1 is also IC1. So we can disconnect completely this transistor and work only on Q1, as we will see. Then we will connect them and work with Q2. So let's start with Q1. So here we will have, this is my transistor. So this is this is 5 kilo. This is RE2. It is basically, sorry, this is RC1, which is 5 kilo ohm, 5 kilo. And this is RE1, which is equal to 3 kilo. Then we have here two resistors, RB1 and RB2. And this is 100 kilo, and this is 50 kilo ohm, and here is your VCC, which is plus 15 volt, and here is the ground. To analyze this transistor, we need to change the look of the circuit. Basically, so we connect these two resistors in parallel. So we will have here 5 kilo. This is my transistor. This is your 3 kilo. And then I will have here the parallel combination of these two, because these two are basically in parallel. They are when you short circuit the supply, so they are basically connected to the same two nodes, so they are in parallel. So the 100 kilo in parallel with the 50 kilo is equal to 33.3 kilo ohm. So this will be 33.3 kilo. And now the voltage here, which is your VB, this voltage VB using voltage division is equal to 15 volt times the 50 kilo divided by 100 plus 50 kilo, and this will give you 5 volt. So this is equal to 5 volt. And this is your plus 15 volt. Now, this is your IB1, IC1, IE1. Okay, now we are ready to start to analyzing this circuit. Okay, so apply KVL here, KVL. So you will have KVL here. You will have 5 volt equal to IB1 times the 33.3 kilo ohm. Okay, plus the voltage drop across BE, it's 0.7. It's not given, you can assume with 0.7. Okay, so it's 0.7 volt plus your IE1 times the 3 kilo. So here we have one equations, two unknowns, but we know that generally speaking, your IB is equal to IE over 1 plus beta. So I can substitute IB with this value. We do the substitution, so you will have 5 volt equal to IE1 over 1 plus 100, which is 1 plus beta, times the 33.3 kilo ohm resistance. So this is your IB times the 33.3 kilo plus the 0.7 plus IE times 3 kilo. Now we have one equation, one unknown, so we will solve for IE1. If you do that, you will find your IE1 is basically equal to 1.29 milliamps. So this is your IE1. Once I know IE1, I can find my IB1, which is basically equal to 1.29 divided by 1 plus 100, and this gives me 0.0128 milliamps. And from this, I can find my IC1, which is equal to the IB1 times beta, which is 100, and this will give me 1.28 milliamps. So I found all currents. Now let me find the voltages and let me see basically. Now I need to find VB1. Okay, so I need to find the voltage between this point and the grounds, which is 0.7 IE1 times the 3 kilo ohm. So let me find VB1, which is equal to 0.7 times the current, which is 1.29 milliamps, times the resistance, which is the 3 kilo, and this will give me 4.57 volt. This is your VB1. Let me find my VC1 here. My VC1 is basically the 15 voltage minus the drop due to IC1. So it will be equal to 15 volt minus IC, which is 1.28 milliamps, times the resistance, which is the 5 kilo. Now, as we know, the kilo will cancel with the milli, and this will give me 8.6 volt. Now, if you come and compare here, this is your NPN transistor. VC is more than VB. VC1 is more than VB1. And if you find VE1 as well, your VE1 is basically equal to your IE1, which is 1.29 times 10 to minus 3 times your RE1. Your RE1, which is equal to the 3 kilo ohm. Okay, so this is approximately is equal to, this is let's say 3.9 volt, approximately 3.9 volt. Okay, so this is less than VB1. So VC1 greater than VB1 greater than VE1. So your assumption that this is in active mode is correct. We started, as you noticed, the question. Now, I didn't mention that clear directly, but it's understood. As far as I use the beta in my equations, it is basically assumed that the transistor is in active mode. So we are done now with the first part here of finding all the voltages of the first transistor. Now let's go and deal with the second transistor. Okay. Now what I know here, let me go back here. Now what I know VC1 here, the voltage here, it's given to me as 8.6 volts. So the voltage here is 8.6 volt. This is VC1. Okay. And also I know that my VB1, the voltage at here, is equal to 4.57 volt. Okay. Now let's find my VE2. Okay, the voltage here. Now the voltage here, you can apply the voltage from VC1. So from this point to the ground is 8.6. And from here to here is 0.7. So your VE2 is equal to VC plus 0.7, which is equal to 8.6 volt plus the 0.7, and this will give me 9.3 volt. So this is your VE2. Now I want to find my IE2. Now IE2 equal to the voltage, which is 15, minus VE2, which is 9.3, divided by RE2, which is equal to 2 kilo. Your RE2 is equal to 2 kilo ohm, and this will give me 2.85 milliamp. So I found now my IE2. From this, we know that IC2 equal to beta IB2, which is equal to beta IB2 is IE2 divided by 1 plus beta, or it is beta over 1 plus beta IE2. Sometimes we call all of this as alpha. Okay, so from this is equal to 100 over 101 times IE2, which is the 2.85, and this gives me 2.82 milliamps. So I found now my IC2. This is my IC2. Once I know my IC2, I can find my VC2. My VC2 is basically equal to the voltage, the current IC2, which is 2.82 milliamps, times the resistance, that RC2, your RC2 is 2.7 kilo, 2.7 kilo, and this will give me 7.62 volt. Okay, so I know VE2, I know VC2, and from this I will find my IB2, which is equal to IE2 divided by 1 plus beta, which is 2.85 divided by 101, which is equal to 0.0285 milliamps. Okay, now your VC2 is equal to 7.62 volt. Your VE2 is equal to 9.3 volt, and your VB2 is equal to 8.6 volt. Now let's see here. This is a PNP. Okay, so your VE is greater than your VB, greater than your VC, so it is an active mode. This is a PNP transistor, so your assumption was correct, and also the second transistor was in the basically the active region. So this is how we can solve a bias DC circuit transistor when you have two actual transistors. One last point here, you see here IB2 is extremely small. The current that originally we assumed equal to 0 is very, very, very small. So that assumption was actually also correct.